Hey everybody, it's Professor Davis here again. This time to talk to you about the molecular orbitals of conjugated alkenes. And to begin our discussion, I'm going to remind you a little bit about pi bonding. First, recall that pi bonds form when two adjacent p atomic orbitals are overlapping. So we've drawn pi bonds in the past like this, where we have our two atoms or nuclei in gray, and there are two p atomic orbitals shown here in white, and they are aligned in such a way that electrons can jump from one to the other, essentially creating one larger molecular orbital in space through which they can move. Now I've shown the electrons here as just doing little laps around one side or the other, and we both know that that's not true. But this is a good way of conveying that there are two bonding electrons in motion within the space created by this overlap, and that is in fact the consequence, the result of the pi bond. Now, what's really interesting is when we have a situation where we have compounds with alternating double bonds. When this happens, a series of p atomic orbitals can overlap, creating a very large region in space through which electrons can move. In other words, if we were to draw two alternating pi bonds in the same fashion that we did before with our isolated bond, the electrons don't just move within their own isolated pi bond, but rather the entire system overlaps, creating a large region in space through which all the electrons can move. This gives compounds with conjugated pi bonds additional stability, and it also gives them some interesting spectroscopic properties, which we can investigate a little bit later in another lecture. So for now, let's just concentrate on the geometry of these pi bonds and how they can form large pi molecular orbitals if they are in fact alternating. I'm going to begin our discussion by showing you a p atomic orbital. Now, up until now, I've been drawing atomic orbitals as usually just one color for one orbital. Actually, I'm going to have to change that now, and the reason I have to change that is that p atomic orbitals have a characteristic we haven't really discussed yet, and that is phase. Now, the phase of an orbital has to do with the fact that the lobe on the top and bottom, as I've drawn it here, are not identical to one another. In fact, one of them is what we call a positive phase and the other a negative. This is a kind of an unfortunate choice of descriptors because really phase could be described as anything that's opposing. It doesn't have anything to do with charge. It simply is a way of saying that one lobe is up and the other lobe is down. Now the consequence of this is that I could flip this orbital over and I could invert the phase so that now the positive lobe is on the bottom and the negative lobe on top. And the way that this affects bonding is that when we place two atoms adjacent to one another, there are two possible orientations now. The p orbitals can be out of phase, or the overlapping p orbitals can be in phase. So now we have two potential ways of combining p orbitals, the out of phase combination and the in phase. When the overlap is out of phase, there is a region in between the two atoms where there is no orbital density, meaning the electrons can't be present at this position. When this is the case, we call this region a node. A node contains no orbital density and therefore no electron density. And consequently, if the node is in between the two atoms, we have a situation where there's a higher energy molecular orbital forming. However, when the overlap is in phase, we have a good bonding interaction where there can be a large amount of electron density between the two nuclei. So this in-phase overlap is what's responsible for creating the bonding molecular orbitals which create the pi bond. I'll be drawing all of these orbitals as simple atomic p orbitals, but we'll be making the assumption that they combine with one another in a linear addition to create the kind of molecular orbitals that you're probably used to seeing in your textbook. Now, for the sake of simplicity, I'll be going back to simply drawing the atomic orbitals which are contributing. And we'll all have to remember as we go through this that these orbitals will overlap to create features that look like the ones on your screen now. Okay, so going back to the simpler representation, let's take a look at some alkenes and see if we can build their molecular orbital sets and use those to start characterizing these molecules. Let's begin with the simplest alkene possible, the molecule ethene, two carbons joined by a pi bond. I can draw this in a three-dimensional representation as such. And if I'm really interested in looking at the pi molecular orbital system, I'm going to have to turn this molecule on its side. So let's do that. When I do that and I place the p atomic orbitals in place, we can see that we have two potential overlapping orbitals here. But we now know from our discussion that the overlap can occur either in phase or out of phase. Of course, the most constructive overlap is the one in which these two orbitals are aligned with one another. When this happens, there are no nodes within the new resulting molecular orbital. So I'm going to place this relatively low on my energy chart here. The second possible permutation is the one in which these orbitals are aligned anti-parallel to one another. And in this case, there is a node directly through the middle of the molecular orbital which will result. So I'm going to place this one a little bit higher on my energy diagram. The last feature I want to talk about is what we call frontier molecular orbitals. If we take the molecule that we've used to construct our molecular orbital set and acknowledge the number of pi electrons present, in this case 2, we can place these within our molecular orbitals following Hund's rule and the Pauli exclusion principle and discover that we have a highest occupied molecular orbital called the pi 1 and the lowest unoccupied molecular orbital called pi 2. This may seem very uninteresting in the case of ethene because there are only 2 molecular orbitals. But as we'll see in a moment here, as the complexity of these conjugated alkenes increases, the number of molecular orbitals and therefore the identity of the frontier molecular orbitals becomes more and more complicated. So let's move on now and take a look at 1,3-butadiene. This is the simplest conjugated organic molecule. Notice that there are pi bonds in alternating carbon-carbon pairs. So I'll draw this as my 3D representation and tip it on its side so we can see the pi system. For further clarity, I'll be removing the hydrogens. So now we're looking at the carbon chain of 1,3-butadiene on its side. If I place my p atomic orbitals in place, I can see that I now have 4 different atomic orbitals which can be aligned. So this will increase the number of permutations of up and down alignment. So let's start thinking about the potential alignments and the number of nodes in molecular orbitals which this will produce. Again, the simplest possible arrangement is one in which they are all aligned in the same way. There are no nodes within the resulting molecular orbital, therefore this will be the lowest energy. We'll call this pi 1. The second arrangement that I'm going to look at is one in which we have 2 up and 2 down on the opposite sides of the molecule. When we have this alignment, we get 1 node directly through the middle of that particular molecular orbital. So I'm going to have to put this one a little bit higher on my diagram. We'll call this one pi 2. A third possible permutation of the up and down alignments is one in which I have 2 nodes. Naturally, because this has an additional node, we'll have to place it higher and call this pi 3. Finally, the last arrangement that's possible is one in which none of my p atomic orbitals are aligned in phase, and therefore I have a molecular orbital with 3 nodes. So 1,3-butadiene is expected to have 4 different pi molecular orbitals. If I look at the molecule, I can see clearly that there are 4 electrons within the pi system, and therefore populating my molecular orbitals from lowest energy to highest leads me to the conclusion that the highest occupied molecular orbital is pi 2, and the lowest unoccupied molecular orbital is pi 3. At the risk of seeming a little bit repetitive, I'm going to do this one more time for 1,3,5-hexatriene. So we've added another double bond to our conjugated system. In this case, if I draw my 3D structure, removing the hydrogens and looking at it edge on, I see that there are 6 p atomic orbitals which can overlap. So when this overlap occurs, there's a potential for a molecular orbital with 0 nodes. This will be my most low energy molecular orbital. We'll call this pi1. I can arrange them in such a way that I have a single node through the middle, and of course we'll call this pi2. If you've been paying close attention, it shouldn't surprise you that the trend continues. We can draw molecular orbitals, each with one additional node, ultimately arriving in a position in which we have 6 molecular orbitals. Right, the highest energy of which, of course, is going to have 5 nodes because we have all of the p atomic orbitals aligned antiparallel. If I populate this system, again, the trend continues. I take my 6 pi electrons, placing them in the lowest energy orbitals, discovering that the highest occupied molecular orbital is pi3, and the lowest unoccupied molecular orbital is pi4. Now, I've only shown you relative energies here, but in the future we'll talk a little bit about how to calculate the exact energies of these molecular orbitals, and that'll be very useful when we talk about spectroscopy. So to sum up, conjugated alkenes have a number of pi molecular orbitals equal to the number of carbon atoms within the system. Notice that we now have 4 atoms giving 4 pi MOs, 6 atoms giving 6 pi MOs, etc. And this trend will continue for as long as we're adding additional double bonds in such a way that the p atomic orbitals are capable of overlapping. Next time we'll talk a little bit about how to mathematically handle the energies of these MOs, and I'll see you then.